Thanks very much, Victor, and thanks to all of you for coming today. It's a pleasure to have you here. So today I'd like to talk to you about how we use modeling for a QbD approach to crystallization process development. But before we go into that, a little bit about Solitek. As we've mentioned, we're based here in the Science Park of Barcelona. And we offer a range of solid-state services. We are a CRO. And so that ranges from solid-state profile, characterizing a solid form, looking at the solubility, the dissolution. It could be solid form screening. We do polymorphism, salt and co-crystal screening. We also work in the area of preclinical formulation. And so our idea here is to provide a kind of bridge between discovery and future development. We will look at the combinations of excipients to get you through that next phase, and possibly including solid amorphous dispersions, which we've heard a little bit about today. We also offer training and consultancy, and last but not least, crystallization development, and that's what I'd like to focus on today. So if we consider the development of a new drug product from, early discovery all the way through preclinical development, through the clinic, and to commercial phases, there's a number of processes or tasks to complete during this. So initially, we're going to be looking at some basic physicochemical characterization. We'll be doing some solid form analysis, XRPD, DSC, this kind of thing. And we'll make an initial evaluation about the performance. If we think that this material, as it is going to give us the desired performance, then we're probably going to move to what we call the main polymorphism study. And here we want to know the main forms and certainly the most stable form to consider for future development. If the performance isn't what we need for stability or solubility reasons, then maybe we're going to consider a salt or co-crystal study. Of course, once we've done the salt or co-crystal, we also have to consider polymorphs of those salts and co-crystals. Again, we'll make the decision, do we have the desired performance? If not, well, we're going to have to start considering some other strategies and other ways to understand the potential challenges we could have for future development. And then around about this time in preclinical development, we'll be starting to look at some of the early formulation studies. Of course, there's going to be analytical development, and then later we're going to perhaps reinvestigate polymorphism to strengthen our IP situation. And so the last box that we're going to focus on today is crystallization process development. And so I've called it stage appropriate. But what is stage appropriate? And following on a little bit from what Alex said earlier, we would recommend starting to think about this as early as possible. And in the next slide, I want to explain why we think that. So here we have a cartoon. I want you to imagine a project team meeting, and we have multidisciplinary meeting, people from different sections who are working together on the project. So the main characters in this discussion today are going to be the R&D scientist, who's been doing the initial work, the plant scientist, who's going to have to take the process and the material from there to develop, and our formulation scientist. So the R&D scientist has already been working on this material. She's done the basic polymorphism work, and she started to look at the crystallization process. And she says, okay, I've got a process. The yield is good, the purity is good. Now let's think about some other attributes like particle size distribution. What do we need? I've said particle size distribution. It could be something else. It could be morphology. Hopefully it's not polymorphism. Hopefully we've already decided the polymorph. But it could be other aspects. So then we move to the plant scientist. He says, well, I'm interested in the filtration and the drying. As long as that works, no problem. Great. And then we have the formulation scientist, and he says, right, it's probably going to be very important, okay? But we don't know what we want exactly just yet. Because why? He hasn't started working on the product yet. And so he's going to receive the material, but the material he will receive to start his initial development is not going to come from him. It's probably going to come from her. Okay? And so then later what happens, several months later, he says, right, I need all of the plant batches from here to have the same characteristics as that initial sample that you gave me to start working on 6 months ago. And this is why we think, we really should be starting to consider our crystallization process at an early stage. So what are our challenges? First of all, the objectives, correct polymorphic form. Obviously, we need to optimize the yield and the purity. And, correct particle size distribution, or at least an understanding of the factors that will affect particle size distribution. Because we have to scale up from milligram scale, magnetic stirring in a vial or a round-bottom flask. We're going to go through jacketed vessels in the lab to make multi-gram quantities, and finally into the plant to a vessel like this. And throughout this process, mixing is changing, residence time is changing, heat transfer is changing. To achieve our objectives here, key things we need to know about are thermodynamics and the kinetics of crystallization. So these are the tools that we have in Solitek to help us with that. Tools from Cambridge Reactor Design, and we're delighted to have with us today Dr. Bashir Haji, who's the founder of CRD, and later he'll be presenting to us some of his equipment, so great to have you with us, Bashir. And the main workhorse in our labs for these kind of experimentation is the Polar Bear Crystal Plus. We like this because it offers us the flexibility of scale. We can work on very small scale, HPLC vials, through to 100 mil reactors we use on here as well. And we get very precise control of temperature and heating, cooling ramps that we can program to do whatever we need. In parallel with this, we have some reflectance measurement tools. This is a system of fiber optics. We have a light source, and then we have another fiber optic that leads to a detector. And we're measuring the reflectance of the particles in our suspension. Okay, this is slightly different to other turbidity measurements, which work in transmission mode. This is looking at the reflectance of the light from the particles. So we have two kinds of systems for reflectance. The first one is a multi-position block for small scale, very useful for determining solubility curves. And then we have a larger probe that can be immersed into a jacketed vessel. And we're working on scales of 10 to 2,000 milliliters. And this is the way we use the reflectance measurements. I'm just giving a simple example here of paracetamol and ethanol. We prepare a vial of a known concentration, and we apply a careful heating and cooling ramp. It's important that this is carefully controlled and accurately controlled, and a slow cooling, slow heating rate. And what we find is as we heat this mixture, at some point we get dissolution. That's our clear point. Then when we cool down again, we have a cloud point where we have precipitation. And what happens is our reflectance gives a profile like this. Initially we have high reflectance because we have a suspension. That drops to a low level when we have solution, and then when we have precipitation again, we regain the reflectance signal. And with these tools, we can have different modes. The standard mode is shown in blue here. That's a very binary mode saying yes, no, we have particles or not. But then there are other modes, fine mode and fast mode. And these are very interesting because they give a more progressive response. And in fact, the response here is related to the crystal surface area. So an example of how we use that. Let's consider two different polymorphic forms, form 1 and form 2. What we can do is we can start with, bottles of the pure form 1, form 2, and we prepare different concentrations in our solvent in different vials. And then we perform the heat-cool cycles that I mentioned before. Slow, controlled heating and controlled cooling. And what do we see? Well, we're heating, so we're starting at low temperature and we're going up here. If we consider form 1, which is shown in blue, then we're going to go through the solubility curve and see dissolution. And by performing the different concentrations, we can quickly plot our solubility curve. And the same thing happens for form 2. Form 2 has a different solubility, it's a different polymorph. When we do the cooling, we don't see precipitation immediately. We see precipitation at a lower temperature. Why? Because we need a significant supersaturation to induce primary nucleation. And this generates what we call the metastable zone. And this is extremely valuable information for process development because, of course, if we want to have polymorphic control, one way of doing that is to seed in this area here where we know that form 2 will not crystallize. If we want form 2, then we should be seeding in this area here. So another example. Again, different polymorphs, form 1, form 2, form 3. This time we see a change in relative solubilities as we change the temperature. At higher temperatures, we have form 2 is the least soluble, and that's another way of saying form 2 is the most stable. Whereas at lower temperatures, we have form 3 becomes the least soluble or the most stable. Again, this is fundamental information that we need to know because, well, first of all, for controlling the polymorph, as we mentioned before, but then there are other considerations. If we're making form 2, clearly we want to seed in this area, but what about the isolation temperature? It might be better isolating at a temperature higher than this point here, where we're going to have competitive issues with form 3, and we might want to know how fast is the conversion of form 3 to form 2 at temperatures down here. Conversely, if we're making form 3, that's our objective, then we have to take into account that at higher temperatures, form 2 is more stable. And you might think, well, what about drying our wet cake? If we dry immediately at a high temperature, then we risk conversion of form 3 into form 2. And so you might want to consider a stepwise drying, firstly at low temperature, and then once most of the solvent is gone, you increase the temperature to dry completely. So again, really valuable information for crystallization process development. So that's the thermodynamic side of the problem. And the next thing to consider is the kinetics of crystallization. Generally, for crystallization kinetics, we consider two main processes, growth and nucleation. Now, obviously, you can't have growth unless you've previously had some nucleation. You need crystal area to have growth. But one thing perhaps we forget is that both of these processes, after that point of initial nucleation, both of these processes are continuing throughout the crystallization process. We have to consider both. I've put some simple equations. These are very simplistic models. You can make them as complicated as you like. But a key thing we notice is that they both depend on supersaturation. Supersaturation is this. It's the difference between the amount dissolved in solution, and our solubility. C star is our solubility. So they both depend on supersaturation, but in very different ways, because this exponent here is different. Typically, G is a lot less than B. And what that means, if we consider the relative rates of growth and nucleation, what happens is at low supersaturation, crystal growth predominates. Whereas when the supersaturation is increased, then we have nucleation predominating. And it's the control of the relative rates of these two processes that affects our particle size distribution, which is important for our formulation development. There are other things we can consider. Attrition, agglomeration. You can add equations here if you like and make the models as complicated as you like. But we're going to make it simple. In fact, we're just going to consider crystal growth. Okay, now remember I said we have both of these processes throughout the crystallization, but we're only going to consider growth. And the reason for that is we're going to be working in this area here. We're going to consider growth, and we're going to calculate our supersaturation. What we will see is that depending on our process conditions, we'll see different amounts of supersaturation. If we see very high supersaturation, then we know immediately, well, our model is wrong and we're going to have lots of nucleation. But it's an indicator that there will be lots of nucleation. So let's go into that in a little bit more detail. Here's a typical profile of a crystallization process. In this case, we're doing a salt formation. We have a binary solvent mixture. Our main solvent is water, and we have an anti-solvent, which is isopropyl alcohol. So probably when we're going to start charging things at low temperature, we're going to heat up. At some point, we have addition of the acid. It could be here, or it could be here. But we're going to go through solution. Why? Because we need to do a polish filtration. This is GMP. We need to remove any foreign particles there. Then we're probably going to cool down and seed. There'll be some aging time, a cooling ramp. Anti-solvent addition could happen here, and a final filtration. And so there are a number of different parameters we can consider, right? There's the seeding temperature, the seeding charge, the particle size of the seeds, the aging time, cooling rate, or volumes. All of these are parameters we have to consider. So our first step in optimizing our crystallization process, the solubility model. In this case, it's not a simple solubility curve because we have a binary solvent mixture. So what we're going to do is we're going to vary both concentration and composition, and we perform the same heat-cool cycles I showed you earlier, and we'll get the clear points. Then we can input that data into a solubility model, and this is a modified Van 't Hoff equation that takes into account the composition of a binary mixture. You regress the experimental data, and you can get the constants, and you have your solubility equation. With that equation, you can do lots of things. With that equation, you can calculate your solubility versus temperature and composition. How much anti-solvent have we got in there? And that's vital for optimizing your yield, optimizing your seeding temperature, optimizing your hot filtration temperature. The next step, we have to consider the crystal growth and generate the supersaturation model. So here I presented a very basic crystal growth equation. It's the same equation we had before, but I've just integrated it so that we can calculate how much solid has crystallized through the process based on that equation. Now, remember, we have low supersaturation, growth predominated. High supersaturation, high nucleation rate. So we're going to look for the supersaturation. That's going to guide us what's happening. Do we have crystal growth or do we have nucleation? And so what do we do initially? Well, we can just use the model, use the equation, and put in some numbers. They're not real, but we're just considering what would happen if I have slow growth kinetics, what would happen if I have fast growth kinetics. We consider all of the parameters of our process, and we put them into a virtual statistical design of experiments. Analyze the data, and it tells us, okay, if we have slow growth kinetics, then it's likely the most important factor is going to be the cooling ramp, and it's nonlinear. If we have fast growth kinetics, the factors are different. We're going to see seeding temperature and the amount of solvent as important factors. And that might be enough information for you to proceed. You might have some previous data, or you might decide, well, based on this, I'm going to do a few experiments and find out which scenario we're talking about. On the other hand, you might want to take it to the next level. I'm sorry I don't have time today to go into extreme detail about this, but if anyone's interested, I highly recommend looking at this webinar from Ran McEwen, who explains in detail this kind of approach. So going to the next level, we need to determine our crystal growth constant, which is Kg. A simple experiment, cooling crystallization. As we cool, this temperature is shown here. As we cool, the solubility decreases. That's based on our solubility model. And we do an experiment. We start cooling. Initially, we have complete solution. And we're taking samples, we filter the samples, we analyze how much is dissolved in those samples. Obviously, if you have PAT technology and online in situ probe, you can do this more easily and generate a lot more data. But this is the way it was done here, by sampling. And we see that initially, we have very little crystal growth. Most of the product is in solution until we reach this substantial supersaturation, and then we suddenly see crystal growth, and the amount in solution is reducing until finally, at equilibrium, we're following the solubility curve. So that's what happens, and then we can fit this data to our supersaturation model. Here's the equation. What happens is if you have different growth, crystal growth constants here, you would see different shapes of the curve. And just fitting this data, we can find out the crystal growth constant for our model. Now, we're going to use that for doing some simulation, but before we get into that, let's consider our process again and the factors. There is an alternative. The alternative is a statistical design based on experimentation. Now, the problem with that is you've got lots of factors here. That's a lot of experiments to include in a full statistical design. It would only be practical to analyze these at a few levels. There'll be lots of analysis. But then we'll generate a statistical model based on our experimental data. That's great, which would be valid within our design space. With the simulation, because we're doing it on our computer, it's all very fast. You can do this on your laptop. You can do all the variables you want, all the levels you want, and do a virtual DOE, go for lunch, come back, you've got your results. Okay? And this is based on a semi-empirical model. We have a theoretical model that we fitted to our data. And that means that our predictions are not necessarily limited by our design space, okay? But you should be cautious. Which is the best approach? Well, I would say it's a combination. I think we should initially consider looking at the simulation. That will tell us which factors are likely to be important, and then we can study those factors in more detail in our experimental DOE. Of course, we're going to need experimental results to back up our model in any case. But combining these two approaches, I think, really adds a layer of process knowledge to your QbD approach to process development. So here's an example of a virtual DOE using our model as before. we've decided to look at that, 9 levels. Easily done on a computer, we could have done a lot more, but experimentally, that would be a lot of work. Cooling rate, we decided to look at 3 different levels. And we're plotting supersaturation here. This is high supersaturation. Well, it's the maximum supersaturation achieved during the process. High and low. Now, probably not unexpected, fast cooling, we have higher maximum supersaturation. That would be expected. But maybe not so obvious is that there is a small window down here where we have minimum supersaturation. And that corresponds to a seeding between 64.5 and 66 degrees. A very narrow window. And probably if you were doing a statistical design, you wouldn't have such a narrow window. You'd be looking at, 64 plus or minus 2 degrees as your levels. So and that would mean that you would possibly miss this effect by doing a statistical approach. I'm going to present, in a slightly different way, a similar model, and it isn't exactly the same. This time we're looking at seeding temperature over different levels and changing the aging time. And here I'm plotting how the supersaturation changes with time. Okay, and what we see is, so here we're seeding at lower temperature, higher supersaturation. What we see initially, temperature is constant, very little crystal growth. But it's significantly more than when we seed at lower supersaturation. And obviously, the longer we leave it here, the more crystal growth we have. And what that means is, when we start doing the cooling ramp later on, in this experiment here, we've already had significant crystal growth at the beginning during the aging time because we seeded at higher supersaturation, lower temperature. And that means that our spike in supersaturation is lower than in the other conditions. So it's something to bear in mind that seeding at higher temperature isn't necessarily going to give you lower supersaturation throughout the process. Initially you have lower supersaturation, but once you start cooling, all of that changes. And this is how the model helps you. So you see the highest supersaturation was under these conditions, and the lowest was by seeding at a lower temperature, a higher initial supersaturation, but by using a longer aging time. And to finish with, we've adapted this model to use with the reflectance probes. The advantage of the reflectance probe is that it's in situ, it's PAT technology. We get lots of data with very little analytical time. Again, I've returned to paracetamol and ethanol, and I'm just showing you that we have 2 different cooling profiles here. So initially we cool down, this is where it's seeded. In the blue one we have initially, in both of them, in the red one and the blue one, we have the same initial cooling ramp, but then we change at this point. This one has slower cooling, this one has faster cooling. And in parallel, we can monitor the reflectance. For the slow cooling, we have this, and for the fast cooling, we have that. And in the dotted lines, we fitted it to our crystal growth model. And you can see that you can get a really good fit of this data to the same crystal growth model that we used before. And then, of course, you can use that for your crystallization development to study the different processing parameters. So some final summarizing thoughts. Please remember that that initial sample that you provide to the formulation scientist could be critical for future process development and could set the benchmark. Solubility curves and models are essential, I would say, for any crystallization process development. And consider using modeling in conjunction with an experimental DOE to give you your full process understanding. Finally, big thanks to the Solitek team who are all here today, and they'll be happy to answer any questions about this or anything else throughout the day. And thanks very much to all of you for listening.
Thank you, Steve. We are a bit short of time. We got time for one question in the audience. No? Going one? Yes.
I have to ask a question. Because I just have to. Yeah. So, obviously, beautiful data and a good alliance between our two companies to show, that the development of a product and its use in developing process can be, as well defined as you have shown it. But the next step, because we're always looking for the next step, is do you foresee a way of automating many of these experiments so that the results come to you perhaps a little bit quicker? Because the time for that definition that you've described has been reasonable.
Yes, it's a good point, Bashir. And initially, there's a big outlay of time to develop those models, to understand the data, and to adapt them to the models. Once you've done that the first time, the next project, the next experiments, it all becomes a lot easier. Clearly, automating that would help. Again, that would be another level of time and effort to develop the automation for that system, which we're not at, but yes. Another level that should be added at some point is to actually look at the particle size distribution and use that data in these models, which adds a whole nother level of complexity to the problem.